Hello, this is Dr. Mode, and today we're going to have another lesson in chemistry. This one's on thermochemical equations. This is now in section 3 of our book. Our scripture verse from today comes from Revelation chapter 20, verses 10. And the devil who had deceived them was thrown into the lake of fire and sulfur, where the beast and the false prophet were, and they will be tormented day and night forever and ever. So the essential questions from this chapter are: how are thermochemical equations for chemical reactions and other processes written? How is energy lost or gained during changes of state? And how is the heat that is absorbed or released in a chemical reaction calculated? A thermochemical equation is a balanced chemical equation that includes the states and the energy change. So as you can see in the reaction, after each reactant and product, in parentheses is the state, and then after the reaction is written, the delta H is given with the amount of energy absorbed or released. So the first heat we're going to talk about here is the heat of combustion, or enthalpy of combustion. The symbol for this is delta H with a subscript COMB, which stands for combustion. This is the enthalpy change for burning 1 mole of a substance. So, for example, if you burn 1 mole of sucrose, table sugar, then it's going to release negative 5,644 kilojoules per mole. So heat is not only absorbed or released during chemical reactions, but when we have phase changes, we also have heat that's absorbed or released. So here we have heats of vaporization and fusion. So heat of vaporization is for the phase transition when it goes from a liquid to a gas, and the heat of fusion is for when we have a substance that goes from a solid to a liquid. So if we look at this table below, we can see for water, which is H2O, that the heat of vaporization is 40.7 and the heat of fusion is 6.01. So for both of these phase changes, these numbers are both positive numbers, which means that when water goes through both of these phase changes, from liquid to gas and from solid to liquid, it absorbs heat, so it will get colder. So we can write these as equations. So you can see here, so for when water goes from the liquid to a gas, we write the state after the water on both sides. So liquid is an L and G is a gas. And then we can write its delta H value of vaporization here as 40.7 kilojoules. And then we can do the same thing for the heat of fusion. When we go from a solid to a liquid, we can write its equation out with its delta H of FUS goes to or is equal to 6.01 kilojoules. So what happens when these phase changes go the other direction? So for example, if we go from a liquid to a gas, we can see that the numbers in those tables previously that we saw were positive, which mean that they get colder. But what happens when we go from a gas to a liquid, or we have condensation happening? Well, what happens is the numbers are opposite to one another. So if you have 40.7 kilojoules that's absorbed for vaporization when it goes from liquid to a gas, then you'll have negative 40.7 kilojoules that's released when you go from a gas to a liquid. Now, the same thing happens when you go from a solid to a liquid. That was the heat of fusion. Those were positive numbers, but when you have the heat of solidification going from a liquid to a solid, then now this is a negative number. So these reverse processes can also be written as equations. The only difference is the letters in parentheses have been swapped, and the values for delta H have become negative values because these actually will release heat and the system will get warmer during these state changes.